Hi guys, in this video I want to start the normal probability distribution. This is a continuous distribution that applies to a wide range of human variables. So it's a favorite of social scientists because not only is it applicable to a lot of social science topics, but it's also something that's very easy to analyze. We're going to see as we progress through this that deriving probabilities once we assume a normal distribution is much easier than if we have a non-normal distribution. When I say normal, by the way, I mean symmetrical. So a normal distribution is synonymous with a symmetrical or bell-shaped distribution. Take a look down here. We've got the typical bell-shaped normal distribution here. The total area under this curve would be 100%, and the mean would equal the median, and that would equal the mode. It all three align. And that would separate the bell curve into halves. So half of our data would be above the mean and half would be below. For example, if this were human intelligence, which we believe to be distributed normally, then this number here, the mean, might be 100. That's the average median mode for intelligence. And then that means half of people would have an intelligence above that, and half of people would have an intelligence below that. Another example of a human characteristic that is distributed normally would be height. So if the average height, the median height, the mode height is, let's say, 5'8", then half of people would have a height above 5'8", and half would have a height below 5'8". Now, even though it's not represented here, on the vertical axis, we are measuring probability. So keep that in mind. So you'll notice that as we look at different values, again, going back to height, if this is the average height, 5'8", well, that would have the highest probability of occurring, which makes sense because the expected value is the mean, and the expected value would be that which has the highest probability of occurring. And then you'll notice that as we move towards higher and higher heights, the probability moving down this kind of vertical axis, the probabilities would drop. Getting somebody that's 6'8" or 7'1" would be, the probability would be very low, right? Similarly, getting somebody that's 3'5" or 4 foot would be very low. And so just keep in mind that with a normal distribution, we are measuring on the vertical the actual probability. That's sometimes forgotten in this analysis. The location of the bell curve of the distribution is determined by mu, which is our mean. So if the mean were to go up, let's say we go from a height of 5'8" as the mean to 5'10", this whole curve will shift. This whole thing will move. Let's see if I can do this here. Let's not try that. But this whole thing will move to the right. The shape would not change. The whole thing would just shift to the right. Or if the mean went down, then the whole thing would shift to the left. The spread is determined by the standard deviation. So the kind of distribution or width, you could say, from the mean to the actual normal curve is going to be determined by the standard deviation. So if you get fatter tails down here, then you would say, well, we have a higher standard deviation because there'd be more people that are really tall or more people that are really short. But if you get slimmer tails down here, then you would have a lower standard deviation. Random variable has an infinite technical range, so even though it may not be real in the world, the fact is in the curve you could have an infinite range of values all the way up to infinity. So height, for example, the average height might be 5'8", but you could have in this model an infinitely tall height. Similarly, you could have an infinitely short height. Again, what is mathematically plausible is not necessarily realistic. Now let's calculate some probabilities given a normal distribution. Take a look at this diagram here. Let's say we want to know the probability of getting a value in this purple shaded area here. So we could make up some numbers. I know we've got letters here, but let's make up some numbers. If the average height is 5'8", and we want to know the probability of getting a value up to 5'10", let's say B, we would be calculating the area here. Because remember, the entire area under the normal distribution is the probability of those events happening, of getting a value up to 5'10". Mathematically, you would write it as the cumulative function, which would be fb parentheses or f510 parentheses, is equal to the probability of getting an x value less than b, less than 5'10". So we've color-coded it here. We'll actually calculate that area in a minute. Now let's say we want to know the probability of getting a value up to point A, this turquoise area here. Well, this area, let's say this A is 5'5". Remember, the mean we said was 5'8", so B was 5'10". So here, let's say it's 5'5". So what is the probability of getting a height up to 5'5"? And we would mathematically write it as the cumulative probability of getting to A, 5'5", is equal to the probability of getting an x value less than A, less than 5'5". Now what's nice about this is if we were to calculate this probability, that is the cumulative probability of getting a value up to B, and we calculate this probability, the cumulative probability of getting up to point A, then we've derived the probability of getting a value between A and B. Because we could just take the probability of this and subtract the probability of this, and that would give us this red area here. In other words, once we know the probability of getting a person up to 5'10" in height and the probability of getting a person up to 5'5" in height, well, we now know the probability of getting someone between 5'5" and 5'10". Next step is to do what's called standardizing the normal distribution. This is effectively going to be transforming our normal distribution with actual x values into a standard normal distribution, which is into z values. For example, let's say we have a distribution here, okay, and let's say, I don't know what this data would be. It could be, let's say, scores on some exam. And let's say the average score is 100 on an exam. Okay, so that's our x value, mu equals 100. And let's assume that the standard deviation for this exam is equal to 50. Well, if we take a value, say 200, and let's assume that you get a 200 on this exam, we want to know what the probability of that happening is. Well, what we first do is convert these x values, 100 and 200, into z values. And the z value for the mean is always 0. Because recall from previous lessons that the z value is how far any data point lies from the mean. You take the data point minus the mean. Well, the mean is 0 distance from the mean. So it automatically defaults to 0 for the mean. And then for 200, that x value, we need to convert that into a z-score. So we plug in 200 as our x value. We then subtract the mean, which we know to be 100. That gives us a 100 difference. And then we divide by the standard deviation, which we assume to be 50 here. So 100 divided by 50 is 2. So we get a z-score of 2. This means that 100 as an x value lies 0 standard deviations from the mean, and 200 as an x value lies 2 standard deviations from the mean. All we've done here is create a different scale of measurement. Instead of using raw data, actual x values, we've converted it into z values. It's going to be very helpful later on because whether we're looking at height or weight or IQ or any other human characteristic, we can always use z values to get our probabilities. That brings us to the z table. This is a table that will help us very quickly get probabilities for our normal distribution. Take this as an example. Let's say that using our previous data, remember we had 100 as our average test score and 200 as our x value. Let's say we want to know the probability of getting a test score up to 200. So we kind of want to know the probability of this entire area here. Well, that's the same as saying we want to know the probability of getting a z value using the standard metric of up to 2. That's what this shows here. The probability of getting a z-value up to 2 would give us the same information as the probability of getting a x-value up to 200. Okay. But z-values are more user-friendly than x-values because we have these nice tables that can convert them into probabilities. So how do we use them? Well, first thing you do is you find the z-value to the 10th place. So we need a z-value of 2, so we're going to scroll down to 2.0, our 10th place. And if we had to go to the 100th place, we would then scroll over to these rows. So if we had 2.01, for example, we go down to 2.0 and over to 0.01. That would be 2.01 or 2.02. We'll play with those a bit later. But right now we've got 2.00. So we're in this row, 0 for the hundredths, and this column. Actually, we're in this column, 0, and this row. And we have 0.9772. What that tells us is that the probability of getting a z-value up to 2.00 is 0.9772. Well, the probability of getting a z-value up to 2.00 is this red area here, which is 0.9772. See? So it's very easy to find these probabilities using the z-table. With that information, we could go back to our test scores here and say, what's the probability of getting a test value up to 200? Well, since 200 is commensurate with 2 as a standard z-score, then we could say it's 0.9772. So the probability of getting an exam value up to 200 is 0.9772. The standard normal table is symmetrical. So once you calculate the probability of one side of the tail, you automatically calculate the other side. For example, if we say that the probability of getting a value up to 2.00 is 0.9772, just like we did, then that automatically tells us that what's left up here is 0.0228. Because remember, the entire area under the normal distribution must sum to 100. So if this red area occupies 0.9772, then the remainder must be up to 100, which is 0.0228. That means the probability of getting a z-score up to 2.00 is 0.9772, and the probability of getting a z-score above 2.00 is 0.0228. Okay? If we were to go back to our x values here, the probability of getting a test score up to 200 is 0.9772, and the probability of getting an x score above, or a test score above 200 would be 0.0228. Some symmetry helps us quickly derive these probabilities. Symmetry tells us that we can also find the probability of negative z-values. In fact, if you're working with a negative z-value, you're just reversing the direction that the table is using. For example, if I go back to the table here, we did positive 2.00, which gave us 0.9772. And that was starting from the left side of the tail and going to a positive z-score. So this area here was 0.9772. But if we want to find a negative z-score, negative 2.00, well, it's going to be the same probability, but you're going to be starting on the other side. You're going from the right tail all the way to a negative 2. Okay. Because it is symmetrical, though, you get the same value. So the probability of getting a z-score all the way to negative 2 is 0.9772, which means the probability of getting a z-score less than negative 2 is 0.0228. All right, that's it for this video. In the next video, I will pick up with the application.